fix some of the sound issues by having me move less and talk more into the cell phone, as well as use the mouse for the videos, for those of you who have struggled to get anything out of those. Okay, so let's begin where we left off in the last lecture, which was to talk about our first matrix multiplication algorithm, which in a sense is quite advanced actually, but also it is very natural to think about. So we can subdivide matrix multiplication into essentially 3D blocks, where each one of the blocks can be, corresponds to a subvolume of computation. So we might have something like ijk, which means that the entry from C is Cij. Live in the top face in this volume cube where essentially every box over here is going to be ijk points. And so A should live here, and we translate lives in space. So effectively, when we're designing matrix multiplication algorithms that are parallel, we're thinking of subdividing this volume so that every processor computes some subvolume. And then the surface area of that tells us something like communication cost. And the most natural approach from what we've seen so far, in particular, we've seen that agglomeration schemes that take on the same dimensionality as the problem we're working with have been advantageous. So it's most natural to say, okay, let's subdivide this thing into 3D blocks that are hopefully of equal dimension. We'll minimize surface area, and we'll hopefully can do everything very nicely. And so long as we have a nice initial layout for A and B, that's not trivial, but we can assume that perhaps we can do so. So we can, for instance, broadcast A along this dimension, which assumes it starts here, but it's valid, and only we need one copy to start somewhere. B along this dimension, compute all of the cubic subvolumes that each processor owns, which may be like this for the top base. And so it will receive all of the B elements, as will the next one down the line here, and all of the A elements. Then finally, we need to do a reduction to sum up the different blocks of C. So these are the 3 steps in this basic algorithm, which works for an N. Does anybody recall what the issue was that we discussed last time with this?
Just the memory.
The memory usage is what will run us into trouble. So let's see exactly what goes on a little bit more. So let's skip these pictures actually and go on to a perhaps simpler version of a 2D algorithm to contrast with the 3D case, where we will instead assign every processor to compute a block of C. And that means that it has to compute everything that contributes to these blocks, all of these multiplications. And so it will then have to all gather this part of A and this part of B from all other processors that owned it initially. So this is the natural algorithm if you think of matrices in the 2D sense. So if you think about blocking the actual memory usage of the matrices and the footprint of the matrices rather than the computational volume. So it is, in a sense, more natural than the 3D parallelization. So here we'll just get everything that we need to compute our block of C and do just that for each of these square P blocks. The problem is, again, to the memory requirements of this algorithm. Yes?
I was just going to ask you, how does memory differ? What memory requirements differ between these algorithms?
Right. So here the memory requirements correspond to the cases of A, of B, and C that each processor gets. And it's a valid question to ask, can you try to compute the same subvolume but somehow stream that data in and do it more quickly? We'll get to that in a second. It turns out for the 3D algorithm, that doesn't really end up making sense. But if we just analyze kind of naively what these algorithms do and assume that all the computation is happening all at once, then here, essentially, the memory usage for a problem of size n will be proportional to the volume of the block P of n that's n squared p to the 1/3, while m1 of n is just n squared.
So our input size tells us that the minimal memory usage should be something like n squared. Maybe asymptotically, or maybe with a factor of 3 in there if you count all the matrices, but roughly proportional to this, while we get that the 3D algorithm will require this much memory. This particular 2D algorithm is even worse, because we've assumed that we're going to grab all of these A elements and all of these B elements at once. As we'll see, that's not necessarily what we have to do. But if we are to do so, we can ask what the memory usage is,
and in this case of the, we'll call it the all-gather algorithm, the memory usage should be proportional to this dimension, which is n squared over square root p. So this is n squared over square root p, and this is n over square root p. Since we need to give a single block of all of the elements of C need to be assigned to some processor, so we need the surface to give size n squared over p. While this is of dimension n, so these two faces are of size n squared over square root p. So here we'll have that the memory usage is n squared root p total.
so it's even worse than p to the 1/3 in terms of overhead. However, we'll realize that in fact we can have less memory. In particular, I think an observation you can make is that if you have every processor compute some cuboid, like where both these and these, as well as something in the middle,
Maybe that looks like this. So maybe just half of
the voxels, its communication cost is effectively given by the largest surface area, or if you will, the sum of the surface areas, which are asymptotically the same, while its memory usage, which area, and this is not a trivial question, but there's only a couple of answers, do you think would be associated with the minimal memory usage for computing that subvolume? So far we've had that the memory usage is also given essentially in line with the communication cost by the biggest surface area. What we'll do is start
subdividing and pipelining things.
marker doesn't work.
And compute only slices
Of this subvolume at a time. And we can do that by accumulating these little outer products, for instance, into C, or little block multiplications into C. So it seems that in fact our smallest face determines how much memory usage we need minimally for this volume. The smallest space is generally the base we can keep local, while these two we can stream in and compute that same computational volume. This is especially easy to see when you're computing blocks of the output. So when we partition this space, it's a little bit more confusing if you think about the smallest space ending up as something like B, on a face that corresponds to B. There you would want to actually keep a block of B local, multiply it by rows of A to compute rows of C, and then probably have to reduce the results for C immediately, or if you're responsible for computing too many rows of C, that will be your memory usage overhead. Okay, but I've stretched kind of, I think, far more into the mixed implication that I should have. Let's return back to the 3D algorithm, and we'll see everything that I just said in more detail over the next several slides. So the most basic way that we can achieve a reduction in this memory footprint for a 2D-like algorithm, so we're partitioning that corresponds to only two of the dimensions of the multiplication cube, is to broadcast these blocks of A and B, so from the side here, successively. One could take that further and say broadcast just a sub-row of A and a sub-column of B and do a little outer product. Although it doesn't really make sense to do it that way, it makes more sense to send some blocks, often proportional So the way this looks like in its most basic form is that we iterate, we take squared p iterations. So our communication now happens in steps. And at these steps 1 through square root p, we broadcast what effectively corresponds to a panel of the matrix A. If we look at it over all the processors, since this I index is effectively parallel over the processor grid, and the row panel of the matrix B. So effectively at step 2 out of 4, for instance, we might compute this outer product, where these two will be multiplied via broadcast this way and broadcast. So we have some 2D processor grid where we are storing blocks of C, and we accumulate to them. And here we, for instance, will multiply a block because this is we're assuming this is the second panel, so we'll assign one index as 2 and the other index as 3. So we'll proceed with these block matrix multiplications at a time. So we don't have within SUMA to broadcast everything that a given processor row and processor column owns. We can pick this block size to be smaller. Or we can even, instead of doing broadcast, do all gathers and pull out different sub-rows owned by different processors. So there is quite a lot of flexibility you can have there. This is just the most basic version of it. And you can also design versions that instead of, so in one type of definition and formalism, this is called the stationary C version of the algorithm. What do you think the 2 other versions would be? So in what sense is this algorithm stationary C?
Stationary A and B.
Yeah, you can have also stationary A and B, which effectively mean that's the matrix you keep local and never move. So here we only ever communicate entries of A and entries of B. We never communicate entries of C. And that is important in a number of ways. In particular, this algorithm so far is really also oblivious, if you notice, to the dimensions of A, B, and C. So these blocks will be square if you're working on a square processor grid with a square matrix, but they may be potentially rectangular, and some of them may be bigger than others. So for instance, if we are doing a matrix multiplication, that looks like this, we want to use the stationary C algorithm and never communicate blocks of C, because the block of C assigned to every processor will just be bigger. We can still imagine blocking one of these on a 2D processor grid. And it will look something like this. So as you can see, each block here is much bigger than one of the blocks here, and they're owned by the same processor. The other variants involving stationary A and stationary B.
But doesn't each processor still need like a block row and block column to compute the
Yes, in particular, for instance, this processor will need everything here and everything here.
And that's not expensive in terms of memory?
Well, if we do one broadcast at a time, we can discard the data after receiving it. So we accumulate into our block. So effectively, the memory usage overhead would come if we collect this block row and block column all at once. But SUMA allows us not to do that. What we'll do is look at a panel of it at a given time, broadcast that, accumulate these A's and this product of A and B into C, and then discard these two blocks. Then we'll go on to the next column and broadcast the next two blocks and store them where we get stored these things. So we need really only storage for one block of A, one block of B, one block of C. That could in itself be prohibitive. That's why you may want to actually take this to be smaller. So if you wanted a very memory efficient algorithm, you would just take a row and multiply it by a column. And the amount of extra data you use would be small. But what would be the overhead of doing that? And the message size would go down, and there will be more messages. So the communication cost will stay the same in bandwidth cost, but will go up in latency cost. There's other reasons you may want to do that, including overlap. And actually also the algorithm where you collect everything all at once sometimes makes sense because it's so simple and so messaging efficient. So if you have a very small matrix that's laid out in a 2D layout, it might make sense to just do a single all gather, do a block multiplication and be done. You may not care about that extra memory. The 3D layout gives you actually a better communication cost, but you have to actually have your matrices line up like this, which is much less natural to applications than the block layout overall is. Okay, and we'll talk about all of these quite a bit more. So, okay, but this is our basic SUMA algorithm, and I was saying a little bit about how you can also try to design variants of it that do not communicate A or do not communicate B. And so those are relevant if you're studying rectangular matrix multiplication. Because some of these blocks may be bigger than others, effectively. But we'll see that also geometrically a little bit from now. And but in most cases, the last thing I wanted to mention is rather than doing two broadcasts, you do a broadcast and a reduction. So in a sense, it's kind of like this is the outer product-based scheme where we broadcast two vectors, while you can also do a matrix vector product-like scheme where you broadcast one vector and reduce the sums of the other. And it makes sense that you would want to do those in those scenarios because a vector is a lot smaller than a matrix. In one case, the matrix is your output, so you have an outer product scenario or an outer product-based algorithm makes sense. In the other case, your vector is one of the inputs, and so you want to block them. So there's analogies there. Okay, so to see that what SUMA does, once again, a little bit more visually, we can think of it as having 4 steps, which are kind of pictured in time here, and doing broadcasts like this of a block column of A and a block row of B on a given set of 4x4 grid of processors. That's really your natural arrangement here. So how would you, using this picture, do 3D matrix multiplication? Or what's the connection between this picture and the 3D version?
Each stage, like each of those 4 stages can be done at the same time on a 3-dimensional processor grid.
Yeah. So if we want to go to the 3D case, as Ed pointed out, we can just think of having 64 processors that are in the 3D processor grid. So we're naturally mapping to a different topology, and we'd be executing these 4 block outer products concurrently, each one on a separate one of the processor grids. And that's a useful abstraction because you can also think about things in the middle. So you can think about having 2 processor grids and mapping half of these to each one, and then your memory usage is half as much as it is in the 3D case, while the communication cost goes down. Okay, all of that is fairly advanced. But before we study SUMA in a little bit more detail, it should be said that there's actually alternatives that have their own advantages and actually are quite a bit older. So in particular, Cannon's algorithm that is all the way from 1969 provides a way to do 2D matrix multiplication in as efficient a way as SUMA, but as we'll see in a slightly less flexible way. And what it does is effectively try to just use point-to-point sends along our 2D processor grid and make everything line up. So we can think of our starting position where we do the coloring as such that we want to multiply all the red blocks here with all the red blocks here, all the yellow blocks here with all the yellow blocks here. So the SUMA algorithm would just take a block row and a block column and broadcast. what what Cannon's algorithm does is it first staggers these, so it does a shift that grows with each one of the dimensions, and it does so to the left and right for this matrix, and up and down for this matrix, and it does so cyclically. So effectively here we stagger this to the left by 0, we stagger this to the left by 1, which puts the red block on the other side. We stagger this to the left by 2, which puts the red block here, moves the blue block 2 down, and stagger to the left by 3, which moves the blue block here and wraps the red block around. Here we stagger up, so again this block stays in the same place. This red block wraps around, the yellow block comes 1 up, the blue block comes 2 up here, for instance, and so on. And after we do that, we notice that the colors line up. So what does that mean? What does it allow us to do?
Local matrix multiplication.
Yeah, we can do a local matrix multiplication between 2 blocks that we want to multiply. So for instance, in the starting layout, this processor owned 2 blocks that it did not want to multiply.
Isn't this algorithm actually better than Summa because it drops the log p cost and the synchronization?
Yeah.
There's no broadcast.
So this algorithm is in theory better than Summa because we've swapped out the broadcast for the shifts. The reason it's pretty much never used in any library is because it's actually quite hard to write an analogy of it for rectangular processor grid, while for Summa it's quite easy. And you want to have rectangular processor grids both to support a number of processors that just doesn't allow you to take a square root, as well as to support rectangular matrices. So as soon as you want to do rectangular matrix multiplication, you want to have a more rectangular processor grid in general, so that your blocking corresponds to the overall computation. And as soon as you try to think about this thing in a rectangular processor grid, life gets surprisingly hard. I've had to implement it once, and I used Trim++ so that I could just create a square grid of virtual processors and then map them to the rectangular grid of processors and let Trim++ do the management of communication. Because you essentially have to start simulating different staggers and shifts within your local data structure, which either you do that yourself or you want to use an abstraction. So yeah, Cannon's algorithm is nice and also kind of quite elegant. In fact, if you allow for kind of send receives that are swaps, so where you can kind of send from the same buffer to which you're receiving, this can be implemented, I think, without using any additional memory. You can just keep everything in place and shift it around, and then kind of shift the blocks back to where they started. So it's very memory efficient, and it's kind of elegant. But in fact, in practice, it turns out to be not all that great. Really generality issues, but also because collectives are that robust, that kind of doing collective with respect to doing a point-to-point message is often not necessarily much worse. There are actually systems on which it can be faster. Surprising. Okay, so there's something also in the middle between Summa and Cannon's algorithm that perhaps also allows a little bit more flexibility and maintains the same theoretical cost. This is called Fox's algorithm. And there you essentially shift along one dimension while doing broadcast along the other. So then perhaps it is easier to adjust how you do the shifting or how you do the broadcast to make things line up. But fundamentally, it's not very much different. And again, the biggest problem with Cannon's algorithm is just the fact that as soon as you want the non-square processor grid, this whole scheme of shifting and making blocks line up becomes much harder to manage. Okay. So let's now do a little bit more formal analysis of the algorithms we've just discussed. So we'll start with the 3D matrix multiplication one, where we had subdivided each dimension into the third root of p, and if we take the cube of every volume, this is our little local volume. Then our broadcast and reduction, assuming that initially A is distributed and B is distributed on a face of a 3D processor grid, is just given by the cost of 2 broadcasts, each of which working on a block of size n squared repeated to 2/3, so effectively the same size as the face, which is in asymptotic notation alpha log p plus beta n squared repeated to 2/3. So again, we don't pick up a logarithmic factor here in broadcast, if we manage the fact that it's actually broadcasting many entries. So the overall execution time, we just add the gamma term back in, but we're not happy about the memory footprint. Locally, we need to store every one of these blocks, including kind of even just our output block C, as well as our initial blocks in the way we define an algorithm. And so those blocks are of size n over p to the 1/3 squared, so one of these squared, multiplied by p because we care about the overall memory footprint. So this is why we were unhappy about 3D. Any questions about that? Okay. So we can then study its efficiency, and we do that in the usual way by effectively putting the expression for time in the denominator and taking it from the other side with p times t1 of n, which is just p times the flops cost effectively. And we get an expression like this, which we can make better sense of if we actually try to figure out how the p's balance out the n's here. So for what type of p will we get 1/3 efficiency roughly overall, for instance. So we in particular need that this efficiency function is 1, and we'll find that we can strong scale by this requirement to a number of processors that's proportional to n cubed over log n, and with respect to latency, and n cubed with respect to bandwidth. So we can strong scale quite far. And that should be natural because we're parallelizing over all processor grid, all dimensions of the problem, and we can subdivide things so that every chunk is basically of constant size. So we can think of this as an agglomeration strategy that breaks things down into constant size k by k by k blocks, and then just collects them on the processors. So effectively, this will begin to stop strong scaling once the cost of doing a reduction is much of just kind of a constant size block is much worse than doing something involving taking that block to 3/2 and doing computation. But that basically depends on the ratio again of our latency and our block rate, the overall volume, and the log factor for the number of steps we need in a broadcast or reduction. Okay. We can also study weak scaling, but that gets to be a little bit confusing when we now look at patient multiplication. At least there's kind of two things we can think about in terms of how we can scale the problem. So we can scale the problem in terms of its volume size being constant per processor, but that does not correspond to the input size being constant per processor, which is perhaps a more natural scaling mode and the one we care more about. So we can notice that, so basically what we need is that this would hold. So as we grow the memory input size, the efficiency stays constant or does not grow. And that will actually hold for the 3D algorithm. So as we grow the problem with respect to the number of processors, which is growing the problem more quickly than to grow the volume with respect to the number of processors. Where if we grow the volume with respect to the number of processors in the same ratio, we'd maintain the same constant size blocks, right? Here we are growing it even faster. So in fact, the efficiency might actually improve a little bit. Does that mean our algorithm, the 3D algorithm, is robust for weak scaling? That we can just use it to solve bigger and bigger problems? Or is there another overhead we'll run into? So our communication cost per processor, relatively speaking, will actually go down as we scale with 3D algorithm. But another quantity will go up. So the local blocks corresponding that each processor will be computing will be growing, right? That's why the efficiency is improving. What else grows as the size of the local block grows? time does grow. So that's one problem. So we'll have to take more and more execution time as we weak scale this regime. But that's kind of inherent to weak scaling matrix multiplication. So as we grow the input size while keeping the input size per processor constant, we do more work per processor. But what else would grow in the 3D algorithm as we keep the input size per processor constant?
Memory.
Yes, the memory footprint per processor will grow because we're doing a larger block on every processor, right? So that larger block has a larger base. So in fact, if we do the analysis, we kind of get the trivial result that actually, yes, it looks perfectly weak scalable in this sense, but if we look at how the memory usage is scaling, especially as we're doing weak scaling, then it will actually grow with p to the 1/3. So effectively, the amount of memory we're consuming per processor will become larger and larger. What we can do instead is ask, okay, what if we keep the memory footprint per processor constant? And this is the memory footprint for our algorithm. So this is not really a scaling mode that we've explicitly considered before. We've looked at M1 over P, which is the input size. MP is the memory footprint for IP processor execution of our algorithm. So this thing can be actually higher. And it is higher in our case. So if we try to keep that constant, we get a weak scaling efficiency that, it's no longer weak scaling. It really is, I think, scaling with work per processor kept constant. And that will eventually die out only when the cost of our reduction, in particular the latency cost, begins to dominate the cost of the local computation. But it's just, that latency cost is in fact quite small. It's just log p. So in fact, it should be very, very scalable in this sense. Okay. So, no questions, let's go ahead. And so we can also derive the isoefficiency function here, which I haven't shown the work for, but and that comes from asking if we want the efficiency to stay constant, how fast does the overall work, the overall computational volume have to grow? And we get a result that says slightly faster than P, so slightly faster than linear. And that is associated with this log P factor is associated with the cost of the reduction, while P would be ideal, so this is close to ideal. Okay, so we can do a similar analysis for maybe this is correct, for what the SUMA algorithm does. So it is also work efficient, although I don't think that's how you get there. But for its communication efficiency, we again basically just have to consider the cost of a broadcast, except now we have to consider the cost of some number of broadcasts. We don't do everything in one step, but we do everything in effectively square root P steps. So we take here square root P, and we multiply it by the cost of a broadcast of n squared over P, which is the size of our local block. So we always broadcast a single local block so that our memory usage stays at n squared over P, because we'll discard it before the next iteration. And the broadcast is linear in cost with respect to this in terms of bandwidth, so we multiply that by square root P and get a term like this. So how much more communication does this require with respect to the 3D algorithm? You know
Peter.
this, let's give everybody else a chance. So our cost there was the same as the memory usage, right? N squared over P to the 2/3, which is less than n squared over square root P. By what factor? P of 1/6. So if you compare this square root P with respect to P to the 2/3, if you subtract 3/3 to get 1/6. So it's a small asymptotic factor. So effectively, this is in a sense why 2D algorithms are not all that bad. They are asymptotically a little bit slower, but not all that much slower than the best you can do. Just p to the 1/6 is that. So the overall execution time is derived directly from those. Okay. And so what else actually went up with respect to the 3D algorithm more significantly? Yeah. More bandwidth and more what else? We don't have more flops, right?
More latency.
More latency. Yeah. By a factor of square root. So way more latency. So we need a substantial number of messages more because we've subdivided the problem into pieces and are doing the translation. While the 3D algorithm really operates all at once. That's actually the bigger benefit probably overall. But it is not mimicked for certain other types of 3D algorithms. And what's nice is this memory, this algorithm is always memory efficient. Okay. So we can then study its strong scalability. We do the exact same trick as before, and now we notice that we have a square root p that's supposed to be canceling in n, and a p to the 3/2 log p that's supposed to be canceling in n cubed in the latency term. And essentially equating these and these tells us how far we can strong scale before these terms start to grow with something proportionate to p, because we're effectively keeping n constant in the strong scaling regime. So that tells us that we can strong scale to at most the number of processors that looks like n squared divided by some log vector. So why is this n squared natural to see for a 2D algorithm? Both latency and bandwidth.
C is constant. You have only one C and just
Yeah,
take
yeah. So if you have more than n squared processors, you would not have any more elements of C. So effectively, this dimension would become 1. So we basically again run out of the partitionings. We get a log factor in there that arises from the latency cost being a little higher, and then we have our usual dependence on gamma over alpha and gamma over beta. So for weak scaling, in fact, life is good. So we notice, in fact, so for weak scaling, we're keeping the problem per processor constant. So we want to keep n squared over p constant. So we increase n with square root p with respect to our kind of n squared over p problem size per processor. And we want to figure out the efficiency for a given number of processors. So we want to figure out essentially as we increase the problem with respect to the square root of the overall problem size or the input size with respect to the number of processors and increase the number of processors, when does the efficiency begin to deteriorate? And we'll, if plugging those terms in, we'll notice that the square root p will cancel with that square root p when we plug in a different n here. So the in terms of the bandwidth cost, the 2D algorithm is perfectly efficient. So it's weakly scalable unconditionally in terms of bandwidth cost for SUMA. While in terms of latency cost, the logarithmic factor is the only bummer. So that is what causes this to show up. So have we actually seen an algorithm that would provide us with perfect weak scalability unconditionally of latency and bandwidth? So what we don't like, again, is just this log factor. It's the log factor and the latency.
Cannons?
Yeah, Cannon's algorithm. So if we do Cannon's algorithm, we aren't doing collectives anymore, and we shut that logarithmic factor in latency cost, and this just becomes what used to be a square root of p, and multiplied by p becomes p to the 3/2. And we actually find out that we are perfectly weakly scalable. How would you kind of
like is the critical path of sending the messages? One for the CAN, just send to
Yeah,
your
for
neighbor.
the critical path,
Yeah,
sending a
you
message.
don't go like log and steps.
Right, so our communication can be done with respect to just our neighbors.
Yep.
And do we have to, but overall, we have to do more communication, right? Because there's more steps. Why is that okay in a weak scaling sense? Usually we've had our communication costs stay constant.
Your latency is constant because you're sending to the neighbor.
Well, we also have to receive more messages, right? Because we have essentially more processors in our processor grid row. So we have to do more rotations at Canon's algorithm. So both the latency costs and the bandwidth costs go up as we do weak scaling in absolute terms as we increase the number of processors and the process size.
But your computation also works.
Yeah, the computation also increases, and it increases at the same rate. So for each message send and for each shift, we do the same amount of work. And then we continue with each subsequent shift. So our efficiency depends only on the ratio of the cost of shifting a message, of a given size, and of doing a local matrix multiplication. We're just doing more of those steps. Our weak scaling efficiency does take into account the fact that the overall computation is scaled, since it is an efficiency metric. So our efficiency will stay constant, but the execution time will go up as we rescale matrix multiplication with the 2D algorithm. So Cannon's algorithm will give us the unconditional weak scalability. It's actually one analogy here to something that happens in the real world quite a bit. So the LINPACK benchmark, which uses LU factorization, uses a 2D algorithm that gets a cost that's very similar. These days it runs for usually 12 to 14 hours on a given new supercomputer just to execute a single LU factorization. Because they've taken that problem and in order to achieve good efficiency, weak scaled it to all of the machine, which maintained a reasonable efficiency, but has caused execution time to grow substantially. Okay. So then we can also consider what happens for 1 gig agglomeration, which is to just partition the mesh in a single dimension, like that. And that should be particularly bad. In particular, our bandwidth cost is proportional to a whole surface. So we need to receive or compute contributions to all entries of a given matrix, which is proportional to n squared. And so we can either have an efficiency function and realize that we can scale to at most n processors, again, just because we can subdivide this only n times. But this is an algorithm that you pretty much never want to do. Weak scalability is slightly better. Okay, then to talk a little bit more about rectangular multiplication, which I've already talked about more than I kind of intended, but it's actually a very interesting topic because while matrix multiplication will be a primitive in a lot of things we do, the rectangular cases of it are even are often, so the matrix multiplications that arise are often rectangular and very non-square in our applications. So understanding how these are done well does help. So what you want to do in terms of a partitioning effectively depends on the ratio of dimensions between the what you're multiplying. So we can essentially have m, n, and k. So the 3 dimensions of these volumes being controlled. And the invariant that we generally want to satisfy is that our partitioning yields blocks that are as cubic as possible. So if we have some long pencil, so what type of computation is this like? So for instance, we call it summa outer product like. This particular parallelization is inner product like that. So it's computing what I would call a block inner product. So we have a very small output, and we are taking something two tall and skinny things and collapsing them together. So, and as for the inner product, we then want to do a one-dimensional block, especially if the number of these blocks can be non-cubic. If we are multiplying a matrix by something tall and skinny, then we want to do, and potentially the matrix is also not square, we want to pick a processor grid that lines up with that. And only once we have all 3 dimensions be large, do we want to subdivide all the processor grid dimensions. In general, we have a kind of optimization problem that's a little bit more complicated than this, but this is the basic thing. Is we want to pick some processor grid as P1 by P2 by P3, and 2 of its dimensions will cut 2 respective dimensions of the processor grid. So K will be cut by P1, M will be cut by P2, and N will be cut by P3. Okay, but that's basically just an intuition for how you do those. And finally, I wanted to talk a little bit about what happens when you, in the memory constrained regime, which I've basically already discussed. So essentially, you can control the amount of memory usage by controlling the dimensions of this smallest space. So the smallest space will effectively tell us the minimum amount of memory that we need to compute that volume. So when all of those are balanced, the smallest space is equal in size to the largest space, so our memory usage is equal to communication cost. When those are but those can potentially be very unbalanced. By controlling their balance, we can potentially make the smallest space larger while making the largest space smaller. So reducing communication cost while increasing memory usage. And so there's a few different ways to achieve algorithms that reduce the communication cost proportionate to the amount of memory you use, well, the square root of that. And those go up until you reach a 3D algorithm. That is kind of the case past which you cannot scale further. So there is a way to interpolate between 2D and 3D algorithms and achieve the efficiency. But we won't really study those algorithms, except I think in a little sense I wanted to talk about the scalability they achieve. So far the cases we've seen for a given amount of total available memory M bar. I call this M bar because M is usually the memory usage of our algorithm. This is the memory available on the computer. So we can ask what we can do with a given amount of memory. If the overall footprint is less than N squared, we can't fit our problem in, so we can say the execution time is infinity. If the memory footprint just allows us to fit the problem in, then a 2D algorithm is optimal. This can be shown formally, and can achieve N squared over square root P. If we have at least this much memory, or in fact more, I should have added omega here, then we can achieve this communication cost and not any better. So one can show lower bounds also saying this is optimal. But for a general M, there are algorithms that actually achieve a bandwidth cost that is dependent on M. In particular, it decreases with the square root of M. And if you plug in those 2 cases, you'll see that this cost fits both of these. So we get a little equation like this for the cost, and for the overall execution time, there is essentially our cost for the 3D algorithm, a latency cost that actually decreases very quickly with increasing memory, and this bandwidth cost given here, and our usual work efficient algorithm. So I won't go through the actual algorithms that obtain this, but this is what we could get. And if we do the efficiency analysis of that, so this is just taking the ratio of execution times, we have memory popping up as something as part of the efficiency term. So now the insight that I want to really talk about is to realize that when you're doing strong scaling, the amount of available memory is growing. So this M bar quantity is growing, while the input size, M1, isn't. Which means that you can actually leverage the extra available memory in order to potentially reduce communication cost. So if you analyze the strong scaling efficiency with this in mind, so you keep effectively the memory usage done by the algorithm proportional to the extra memory available, we can show that the efficiency will actually stay at theta 1, and that will scale. And those otherwise will need this equation, and we'll obtain that the number of processors to which we can strong scale is proportional to something like n cubed over log n. So dependent on n cubed. This is the same equation we saw for the 3D algorithm. Except that the 3D algorithm in the strong scaling case may have required at some point more memory than was actually available. While this is in a sense always memory efficient, and achieves as good of a strong scaling in the sense as the pure 3D case. Okay. Any questions about mesh duplication? I think this is the last slide. The intuition for partitioning these different problems that arises there is very valuable in other algorithms. You have to solve basically the same problems except it's harder.